let's start.
Check.
Everybody, it's 9 o'clock now, and I think 9 o'clock in the evening in America, at least in the East Coast. Welcome you, to this second part of the talk on astronomy of neutral atoms. We have two experts. One is Professor Johnny Shea. He gave a talk already a few days ago, but he will give second part of his talk in a few weeks' time to be arranged. Time still be arranged. And today's talk is to be given by Professor Eberhard Möbius. And I think we knew each other for a long, long time when I was in Lindau and you were in Garching. But let me say this, according to his CV, Eberhard got his PhD from the University of Bochum in Germany. And he spent 12 years at the Max Planck Institute for Extraterrestrial Physics, working on a number of important projects, including MT, IRM, I think FAST also, right? And
FAST, no, that started when I transitioned to New Hampshire.
Okay, so and he, after 12 years at in Garching, Eberhard joined the Space Science Center and the Physics Department of the University of New Hampshire, making the UNH a very strong experimental group actually at that time. So he started there in 1990. And as you heard, he immediately during the transition, he started working on the FAST and cluster, SOHO, ACE, stereo, IBES, and now IMAP, and all those are very classical pioneering missions, with sophisticated instrumentation, partly contributed by Eberhard. Because of IBES and IMAP, Eberhard turned his attention from meteospheric physics to interstellar gas and its interaction with the heliosphere, in particular using the ENA imaging. And he's going to talk about his experiment, I believe, on IMAP. And a year or two ago, I met the Martin Lee, and he told me that you're so precise that your requirements driving him crazy, you know.
Yeah.
That's for you to settle.
Yeah, I know what he means.
Eberhard is AGU fellow, which is very important in our field. And he received several important NASA and ESA achievement awards. And at UNH in the University of New Hampshire, he received several honors, including the position of distinguished professor. But I think that he has still a lot to talk about, you know, and I hope that he will continue. And then if not enough time, and I'm sure that he's going to give another talk. Eberhard, go ahead, please.
Thank you very much, Wing, for this opportunity to talk about IBEX. At the end, I will say a few words about IMAP, which is to be launched next year, actually. So we're kind of working hard on that one, but we are enjoying the science of IBEX, which is up since 2008, still working fine, and we are hoping for an overlap. So you see the IBEX team here, and the talk will be about astronomy with neutral atoms, and I will try to explain what that means. And the two topics that I selected is imaging the heliospheric boundary and catching the interstellar wind with the interstellar boundary. That's what this IBEX, the acronym, stands for. And so, okay, I'll have to click here. Maybe, yeah, this is my first lecture in Taiwan, only virtually, but it's interesting that we can do these things via Zoom. It's not Zoom, it's Google Meet. So If something doesn't work, blame it on the fact that this is the first time for me with Google Meet. First, I want you to meet our mascot, the ibex. So these guys are roaming around in the Alps and also in the American mountains. So you see, ibex is not just an acronym, it's a real animal. And now that you know the ibex, I could stop here. And so do you know what ibex is? But instead, let me take you back more than 400 years. That's when astronomy changed from just using our eye power to some additional gadgets, namely in this case, the telescope. And Galileo was the first one to put it on celestial objects in 1609. And exactly 400 years later, after we had expanded our view already across the electromagnetic spectrum of which the visible that we can see with our eyes is only a sliver, basically to infrared, very long wavelengths, and even radio astronomy, and on the other side to gamma rays, very high energy, very short wavelengths. And you see a depiction of the Milky Way here in infrared and gamma rays. I'll come back to that briefly. And we were just in time for the International Year of Astronomy, namely we commissioned this little satellite with its 2 instruments in 2009. And now let me put the neutral atom astronomy into perspective. With photons or electromagnetic waves, we have the ultimate horizon at the background radiation, which COBE, another explorer, IBEX is an explorer satellite. So NASA's very successful mission line that started with Explorer 1 that found the radiation belt of the Earth. And COBE mapped out for the first time the full scope of the background radiation, which is the horizon for electromagnetic waves. Beyond that, we can only poke with neutrinos and gravity waves. So that yet needs to be done. But with neutral atoms, we can do local astrophysics. They reach to the boundary of the heliosphere a few hundred astronomical units, 1 astronomical unit being the distance of the Earth from the Sun. And here you have one diffuse source, that's the boundary of the heliosphere, and one point source, that's the interstellar gas flow through our system. Now, with IBEX, we are basically turning this technique to its horizon. The good thing is that with such a new animal, you are always worried about, do we see something else that interferes with what we want to see, namely the boundary of the heliosphere. There's no such thing, no interference from farther away, because that's where it becomes optically thick for neutral atoms, and you don't get any information from there. The other good thing is neutral atom imaging basically connects space physics, that's where we have our satellites in, and astrophysics, because we are connecting to the local interstellar medium and its interaction with the heliosphere. Just a little tidbit that I put in just last week when I got my belated issue 8 to 9 of the Physik Journal from Germany, and it had this figure in it, the galaxy, the Milky Way galaxy in the visible, in gamma, as you saw before, and underneath in neutrinos. So that's the other new kid on the block for neutral particle astronomy, that we can basically get directions for neutrinos from the ice cube measurements on the southern pole. And here you see an artist rendition of this neutrino picture overlaid on the visible one. And this is from the February issue of Astronomy. So that those are measurements that were puzzled together just last year. So you see, astronomy gets more and more tools, and the neutral atoms that Johnny and I wrote a book about, which Wing Ip invited us for, is the new kid on the block for our local astrophysics for the heliosphere and the local interstellar medium. Now, you might ask, what is it good for? And I always put that in terms of 3 important points. Namely, it's a matter of comprehension. We need to comprehend or understand the local environment where space weather plays out. And then it's very important to see that the Earth has actually 3 shields against high energy cosmic rays, namely the heliosphere with the solar wind blowing out the sun's magnetic field, which produces a big shield, the Earth's magnetic field, and then the Earth's atmosphere. Without these shields, we wouldn't probably be here, because everything would be so radioactive that life either may not have evolved or may have taken a totally different course. And if we look at our astronauts, the ones going to the moon again and maybe further to Mars, they only have 1 shield, namely the heliosphere. And that's what we want to understand. Number 2, it's a matter of investigation. And here we start at the sun, which is a typical star, but the only one with a close-up view, and the heliosphere is the astrosphere, the only one with a close-up view. The interstellar medium around our heliosphere is the original star stuff, meaning stars, planets, and us ultimately have evolved out of interstellar material. And you see the Eagle Nebula up on the right. That's a very famous star-forming region. And on the lower left, you see a supernova explosion. And supernovae are the ones that change the composition of the interstellar matter. And if we can compare the matter in our solar system and in the interstellar medium, we have actually 3 points in time, if you include the Big Bang, when you only had hydrogen and helium. The sun formed out of interstellar medium 4.6 billion years ago, and the interstellar medium is the star stuff as of now, the current Milky Way galaxy. So you have a timeline of evolution where in between supernovae sprinkle new material in there and change the composition. And also other stars have astrospheres, as you see in the Hubble picture to the lower right. And finally, it's a matter of exploration, where we haven't gone yet. And no exploration has ever come back without new discoveries and surprises. And I can assure you, we've got a number of surprises with IBEX. Now, if you want to see our heliosphere from the outside, like with the Hubble telescope seeing this astrosphere, you have to do that with something else than light. But I put a flipped over astrosphere here, BC Camelopardalis, to illustrate how the motion of the sun through the medium, that yellow arrow, and the motion of the local interstellar cloud come together to the vector velocity, the yellow line, and that produces an interstellar wind, this motion relative to each other through our system, and it shapes the heliosphere like a windsock. By the way, this beautiful picture is from Priscilla Frisch, who is one of our collaborators. So we have to image the heliosphere from inside, since we don't have an interstellar probe yet, and we cannot do it with light. So we resort to energetic neutral atom observation. Why? I started when I decided what I wanted to do in physics, to study plasma physics. Why? Because at that time I learned more than 99% of the matter in the universe is in the state of plasma. Of course, we know that this is only 99% of the 4% that we know what it is, and the remainder, dark matter and dark energy, we don't know yet at this point what we are really talking about. Okay, but I studied plasma physics to get into astrophysics and space physics, and here we are, and I have reverted going to neutral atoms, because charged particles don't make it to 1 AU if you want to see what goes on at the heliospheric boundary. But the plasma out there sees this interstellar wind of neutral atoms blowing through, and once in a while you have a collision between an ion and an atom, and then you have a fairly high chance that they exchange their electron. So the neutrals from the interstellar medium lose their electron to give it to the ion. And here's this nice joke about two atoms walking along with the interstellar wind. In this case, all of a sudden goes the one, you know what? I just lost an electron, says the other one. Are you sure? Yes, I'm positive. So that one got positive, but the positive ion moves on as a neutral, and now it isn't bothered by magnetic and electric fields anymore. It goes straight like a photon, and if it doesn't bump into something, it can even go to 1 AU. So it goes straight. And if you have the right detector, you can catch these ENAs, and if I blow up this formula, you see the information in red that we want to get, the holy grail of plasma physics, namely the distribution, the velocity distribution function of the ions in this case. And we get that in the form of the differential flux of the ENAs as a function of energy. And we measure the direction, namely the look direction of the instrument, and how we get the full sky. We get to that in a minute. And then there is this cross-section that's energy dependent, with which the density of the neutrals, the interstellar neutrals, gives a certain probability to turn these ions into neutrals. And you multiply that by the field of view of the instrument. And of course, you are getting a line of sight integral of the region where the plasma is, maybe the inner heliosheath. And you have to integrate from the inner to the outer boundary. And if you can measure the density of the interstellar medium, which I will get to because our instruments measure that as well, then you can, in this case, even compare with the local measurement of the voyagers of the distribution of the ions. And you can deduce, for example, the thickness of that plasma layer, the heliosheath, between the termination shock and the heliopause. And as I said, the interstellar wind blows through, and we can measure that directly. And where the interstellar wind blows through outside the heliopause, it also generates some new neutrals from that region. So we get a pretty good sight of the boundary region of the heliosphere. Now, how do we do that trick to get an image of the interstellar medium? So you see the IBEX satellite with the two instruments here, which are two huge single pixel ENA cameras. Now, with a single pixel, that doesn't give you an image. So you have to do something with these pixels. So we take advantage of the fact that we have put that on a spinning satellite. And I'm sitting on a spinning stool here. If I take my arms pointing out like these two instruments and I'm spinning, you see I'm scanning a line on the sky. And that's what this animation takes. And you see that line in the sky, and to the right up there, you see Jordi Laforge, that blind engineer who wears a visor that he can see, and he can see more than we can see with visuals. So in each of the sequels, he sometimes switches to different things, and I'm sure he has a switch that he can switch to energetic neutral atoms, if that suits the bill for one of the sequels of Star Trek, The Next Generation. So that gives you one strip, one slice in the sky, and you see that depicted here. But IBEX orbits the Earth, and the Earth orbits the Sun, as depicted here. We built IBEX as a sun-pointed spinner. Number one, we have our solar cells on the front side that needs to point to the sun. And number two, and more importantly, we don't want to look with our sensitive instruments into the sun or into the solar wind. So we put it at 90 degrees, and that's where we want to keep it. So what we do is every orbit, which in the beginning took 7 days, it moves about 7 days in angle, 7 degrees in angle, sorry, but 7 days of 365. It's almost 7 degrees. That's the width of our field of view. So now you get a next strip in the sky and a next, and you do that for 6 months. So you get a full sky viewing with a few places blocked out, for example, where the magnetosphere of the Earth gives us a lot of foreground that we can't look through for the heliosphere. And here you see in the animation how Ibex moving around the sun with the Earth produces this neutral atom picture with a simulation that we put into our proposal. That was the idea that theorists came up with, but I can tell you it didn't look like that. So, but I will come to that. Now, how does our visor work? Remember, Geordie LaForge wears a visor, and I like it to compare our ENA instrument to a visor with which we can see neutral atoms. Number one, we need to remove, and a lot of this, I'm sure Johnny has talked about a week ago, but I want to just point out the most important things that we have here, and these are the components of our instrument. So we have a collimator that at the same time removes electrons and ions, which are plentiful out there compared to the neutrals. In that plasma of the solar wind, neutrals are basically a needle in the haystack, or even worse. So we need to remove them with deflecting them with an electron repeller, and we put the collimator on positive voltage. So that removes the electrons and ions. And then the collimator, I will show you in an animation how that works, to let only through particles in a certain field of view. What you get is the ENAs and a lot of UV photons, and those are distractors that we need to get rid of too. Next, we use a trick, because neutral atoms are very hard to analyze. They don't tell you the energy or the mass unless you turn them into ions again. And for the higher energy, we send them through a very thin foil, an Ibex high, the higher energy instrument. And for the low energy one, they would get stuck even in the thinnest foils. So we bounce them off a very smooth surface where they pick up an electron and turn into negative ions. So the high energy instrument uses conversion to positive ions, and for the low instrument that I will be talking mostly about, the negative ions. So at that point, you still have lots of neutrals that make their way on, since that conversion is not perfect. You have the photons, the UV in there, and you have the converted ions. Then you send it through an electrostatic analyzer, which selects the energies. So that's where you get the energy band from. And then you send it into a time of flight mass spectrometer for Ibex low, meaning we measure the speed, and with the speed you have the energy per mass. From the electrostatic analyzer you have the energy per charge, but you can only get one electron on the neutral, so it's always singly charged, so you have the energy. You have the total energy here, energy per mass, you can back out the mass. And IBEX high doesn't do that, but it uses basically a time of flight spectrometer for coincidence measurement to weed out the background. So low and high have basically the identical in step 1 collimator, and the step 3, the electrostatic analyzer, and step 2 and 4, they work slightly differently. So the collimator is a stack of grids which only lets particles through in a very narrow angular range. And you see the test with the prototype here in Bern. You see that's the prototype. So we made hexagon grids, and you see as you tilt it what the detector sees. So now it's fully open, and then it closes again, and you see when it comes to 7 degrees, it's shut. And you can go further and further. There are enough grids in there so that particles cannot slip through even at larger angles. So that's the first step. And then for IBEX low, these collimated neutrals hit the conversion surface. You see a sample here in the center, and that's diamond-like carbon. That's a layer that was very well known and widely used when we built IBEX, namely as the protective coating for hard disks. Now in the computers, hard disks have almost gone away in lieu of solid-state memory. So here we could basically take a technique that was widely available in the industry. Then we bent the path of the ion through a band pen-shaped electrostatic analyzer. You look into the outer plate here, which is pitch black, so that you can suppress sufficiently the UV photons, which would otherwise create a tremendous background. And then we go into a time of flight measurement where we actually measure the time of flight 3 times so that we have superior background and noise suppression. So with that instrument was launched in October 2008. And here you see a measurement from one of the first orbits where we said, wow, this instrument is looking at the moon. We can see the moon in the light of energetic neutrals. And that was a big surprise, but it also helped to prove out the instrument working. So that came at the right time. So you see the orbit of IBEX, highly elliptical, up to 50 RE. That came within 10 RE Earth radii of the moon. And that's when we saw the moon signal. And it was interesting, the intensity of this neutral flux correlated very beautifully with the solar wind flux. So very clear, solar wind hitting the moon produces neutrals. And the lunar albedo for energetic neutral atoms is about 10%. And because of that, the moon emits about 150 tons per year of hydrogen. By the way, these neutrals become ionized again in the solar wind, and this was something that we have seen with my very first time of flight spectrometer that I built in Garching, the empty Soleika instrument, and this Hilchenbach et al. Paper, who took over from me in Garching when I left, and so he coaxed this out of the instrument. So as I said, this measurement demonstrated the high sensitivity and energy resolution and low background of the IBEX observations. And now with that, let's move outward to the heliospheric boundary, where just before IBEX launched, after a 30-year journey, the Voyagers had finally reached the termination shock. After everybody was wondering when will they finally hit the termination shock. And they returned some surprises. So that was not, the two Voyagers didn't see it at the same distance, telling us that the heliosphere is squashed by interstellar magnetic field, which needed to have a strength between 3 and 3.6 microgauss, with the direction tilted by 30 to 60 degrees relative to the inflowing interstellar gas. And this direction that was seen was consistent with an offset of the interstellar hydrogen flow relative to helium that also had just been seen. So there was a lot happening, but big pieces of the puzzle were still missing because the termination shock is a huge entity enveloping the entire heliosphere. But what the heck is the termination shock? Well, in a nutshell, it's the supersonic boom of the solar wind, where it is being stopped by the interstellar gas. And you see and hear a supersonic boom with the cracking of the whip. So what Indiana Jones is great at. And I learned about that first as a young postdoc at a cosmic ray symposium in Bologna, where I happened to sit next to now it come Ian Exford, and he, so when they were coming on the stage, whipping the cracking the whip, Ian Exford told us, you know what that is? That's the supersonic boom. And I've never forgotten, and let me see whether in this room I can do that and you can hear the, that wasn't good. I have to stand a little bit. I hope you heard the crack of this whip. So I can create a supersonic boom even in the room, and hopefully you heard it over the internet. Better known, the supersonic boom with supersonic aircraft, and here is even a visible depiction of that supersonic boom with the aircraft flying by an aircraft carrier. Now, the termination shock is a three-dimensional entity, which is hard to picture, but this experiment in our kitchen sink illustrates that. So you see the water flows in the center, that's where the sun is, out flows the supersonic solar wind, and then where it stalls, that's the equivalent of the termination shock. And you saw it's slightly slanted where it goes towards the sink. That would be the equivalent of the interstellar flow. Now, with the Voyagers, 2 of them, we had 2 points of the termination shock, but the rest we didn't know. That's where IBEX came in. And after we had the first half year of data, we said, wow, who ordered that? We didn't expect to see such a bright structure in there that we termed the ENA ribbon. And the Voyagers just missed that. So they didn't fly through that, or not flying through that. Now, with our 2 instruments, we had the validation because both of them, with a different way to get the ENAs, saw the same thing, although IBEX low has a much lower statistics because it's tuned towards the interstellar flow. Now, the question was, what is it? And discussing that in a meeting, Priscilla Frisch was the first one to say, oh, this looks like it's in the direction in the sky where the interstellar magnetic field is perpendicular. And at different energies, we see a different pattern. And that basically showed us the possibility, it's the locus where the interstellar magnetic field and the look direction is perpendicular to each other, or B dot R equals 0. That was the first hint. So then we had a big brainstorming session, and out of that evolved about a dozen different ideas how this ribbon could be generated. And with more and more data, it became clearer and clearer that the solar wind was pretty much directly involved. And there were 2 of the ideas, one at the termination shock and one beyond the heliopause that I will talk a little bit more about, that fit that bill best. And with over a few years, we even got depths into that. Namely, if you see that pattern here, it's most intense near the equator at 1.1 keV. And if you go to higher energies, it's more pronounced at higher latitudes. And that's the pattern of the slow solar wind in the ecliptic plane and the high-speed solar wind at high latitudes. If you go to solar maximum, that pattern goes away because the solar wind isotropizes, and we could use the delay of the change of the solar wind to get depths, and that fit very well with a parallax measurement that painstakingly Pavel Swatzina did. And that put the ribbon basically at or beyond the heliopause. Now, the model that seems to fit the bill the best is the so-called secondary ENA model, where the solar wind turns neutral through charge exchange, and the neutral solar wind goes out into the near interstellar medium. And where it's perpendicular to the magnetic field, when you generate pickup ions, they accumulate in a ring. Whereas if you are at an angle of the magnetic field, the pickup ions disappear on a spiraling motion. So that explains why the the ribbon is so bright. But the pickup ion ring should be affected by instabilities, and you need a long integration to get that intensity. And the question was, does that work with the time variation that we see? So about the instabilities, there were a number of different ideas that basically got that reined in. And I think the currently best idea seems to be that the waves themselves retain the pickup ions spatially by Schwadron and McComas. So I will skip a few slides here to not make it too long. The interesting thing is that the direction of the magnetic field works to explain the high energy cosmic ray anisotropy. So TeV cosmic rays that you get with IceCube and the Tibet array. And with modeling, you can show that the observed anisotropy is due to largely the streaming of that steep spectrum, and some of the structures that you see are really local due to the disturbance by the heliosphere. Now let's turn to the interstellar velocity. And the first question to ask here is, how can we catch the wind here at 1 AU? And if you would have asked an astronomer before 1967, they would have told you, that doesn't work. Don't you know that we are living in a Strömgren sphere? Like you see here for the Rosetta Nebula. And that means that the stellar wind, or in our case, the solar wind, would push out all the ions that are generated by the sun's UV, and you can have neutrals only beyond 700 astronomical units, way outside the heliosphere. But that forgets about the motion of the sun through the interstellar material, and Hans Fahr was the first one to point that out. And if you take that into account, then you get ionization much, much further in at the sun, and that this material survives. I want to demonstrate at this candle. So I hope you can see the candle. Yeah, I see it in front of me. Now you wouldn't think that I'm so stupid, put my finger into the flame and see it burn up. Well, no, I don't do that, but I can go through the flame quickly. I hardly feel the flame, and that's basically what happens to these neutrals. There is not enough time to ionize them. And here I had my lucky day with my first instrument, Soleika, when we did our first release of lithium canisters, which produced neutral lithium in the solar wind. And I could see a few lithium atoms, altogether 7 in overall energy range out of 10 to the 25. That was good enough to give us a paper. But more interesting was that we saw mass per charge 4, singly charged helium, which normally wouldn't be in the solar wind because that comes from a 1,000,000-degree hot corona. But these guys are coming from the same direction like the lithium that we just put in. And so we identified them as pickup ions. So you see it depicted here. If you put a neutral atom into the solar wind, it starts with velocity 0. Now the ion can only gyrate around the magnetic field, but that magnetic field is swept away with the solar wind. So the pickup ions get a speed up to 2 times the solar wind energy. Think of this ring as a wheel that touches the road where the speed is 0, and on top of the wheel it goes twice as fast as the car. So that's the highest velocity, and you see that cutoff of the distribution at 4 times the solar wind energy or 2 times the solar wind speed. Now we saw that filled in. We didn't just see them at the solar wind energy, because scattering fills the shell, and then it expands with the solar wind, and it cools, so you fill the full shell. And that's the distribution that we saw. So that was the first way to get at interstellar neutrals via pickup ions. But now we have IBEX, and we can see the wind, and you see Scorpio, Sagittarius, and Libra. And here you see that sky view, and the red, that's where the wind comes from. And the X is the inflow direction outside the heliosphere. So why is it deflected to the side? I need to go to the next one. That's the sun's gravity. So the flow trajectories get deflected. Slower ones less, stronger, and faster ones get deflected more. So we can use the sun as a gravitational spectrometer to get the inflow direction, flow speed, and the temperature. And here you see that we get the interstellar flow each spring for helium. Hydrogen, you see it's a slightly different direction because hydrogen sees the radiation pressure, and oxygen and neon. We didn't expect to see neon, but we finally saw that. And we have this broad distribution and an extension for oxygen, which we identified as the so-called secondary component that is produced in the outer heliosheath. So oxygen and hydrogen decrease with solar activity, but let's concentrate now on this broad swath that we see to the right, only at the lowest energies. At the higher energies, that's not visible. That's the secondary component from the outer heliosheath. And that is deflected, and we can see, interestingly, it's from the helium deflected towards the direction where the center of the ribbon is in the sky, which is the direction of the magnetic field. And both oxygen and helium, after a few years of data, go along this line. So if you see the blow up, that's amazing how well that's aligned, and the oxygen seems to be even deflected a little bit the primary in the other direction. Now, starting with the measurements, we got pretty wide error bars because we can see the interstellar medium only for a month or so in the spring. So we have a very limited vantage point. And there's a large error along this line, which we coined the parameter tube. And our measurements seem to be different what Ulysses Gas was saying, but we identified that our sensitivity to that secondary component basically jerked our measurement in the one direction, but that was additional diagnostics of the outer Helios sheath. Now you would want to have a measurement that cuts basically almost perpendicular through that. And with pickup ions, we had identified something like that in around 2000, namely the cutoff of the pickup ions nominally 2 times the solar wind speed. So if I just take the solar wind speed, that forgets about the interstellar wind. And that's substantial at 1 AU, about 50 kilometers per second. So it's about 10% of the solar wind speed. And if you are upwind, they are opposite to each other, and downwind in the same direction. So downwind, you have to subtract the ISN flow, and upwind, you have to add it, because the pickup ions are generated in the solar wind frame of reference. And with SOHO and EMTI, we had the measurements on both sides, but in order to do that as a quantitative measurements, you have to have observations year-round, and we got that from stereoplastic. And you see this beautiful curve which goes along the blue line, which is a very simple model with very small scattering, upwind and downwind. And you can basically flip that, and you take advantage of the symmetry, and then you get a very small error. Of course, there are a number of systematic errors, and there are 2 papers that brought down these systematic errors to about 0.35 degrees. Now, with combining these neutral measurements and the pickup ion measurements, we could do it so precise, and with Ulysses, that we could finally say, we are not in what astronomers call the local cloud, the very closest one. We are actually between 2 clouds. And you see the astronomical measurements for Redfield and Linsky, looking through these clouds towards nearby stars and doing absorption line measurements. And to the right, you see the velocity vectors and temperatures for these 2 clouds, the G cloud in the direction of the galactic center, and basically to the back, the local cloud, and in blue, the measurement that we got with IBEX, Ulysses, and stereo, and it falls right in between. And if you do a statistical analysis, with Swachina has done, it's very unlikely that you can put it into either one of the clouds. So the verdict is we are in an interaction region between 2 clouds, and we kill basically 2 birds with 1 stone. Namely, there were the conundrum that the local density that we measure right here seems to be twice as high as the astronomers get for either one of those clouds. Only two stars that are perpendicular to the interaction line of these two clouds seem to have that high density. And that's kind of looking through this lens where the interaction happens and where the two clouds are compressed. So not only do we reach out in the interstellar medium, right there we have interaction physics. So we can start to work on interstellar cloud collision physics, study the draping around the heliosphere and the deflection of the plasma around the heliosphere in the outer heliosheath. And doing that by measuring the flow vector and the interstellar magnetic field from the ribbon observations and putting it all together with the secondary flow in the outer heliosheath. With IMAP, we will do that with higher resolution and sensitivity and better coverage, because we put that spacecraft into the Lagrange point L1, and launch will be next year. And with an L1, with the instrumentation we have, we even give the magnetospheric community a detailed input what's coming from the sun. And with that, I want to thank Stevie Wonder for this song, The Ribbon in the Sky. So this blind singer apparently knew something that we didn't know yet until we launched IBEX. And I would like to acknowledge all the funding we got for this wonderful project. Thank you very much.
Thank you so much, Eberhard.
Yeah.
I'm sorry that you finished right on time. Otherwise, I was looking for the second part of your talk.
Yeah, but I cut short any questions, I guess.
Okay. I think one question I would really want to ask you is that, do you think that you can use ENA with IMAP to determine the shape of the heliosphere?
Yeah, the shape of the heliosphere, well, what I didn't talk about is the so-called globally distributed flux. So I highlighted the ribbon and the interstellar flow and the secondaries. The fourth kid on the block is the diffuse component that's all around, and that was the one that was modeled in this model depiction of what we anticipated to see. But we couldn't get at this until Nathan Schwadron had devised a method to subtract the ribbon. And meanwhile, there are, I think, half a dozen different methods that are very complementary. So you have to take that out, and then you get this this component. And this one is basically the ENAs from the inner heliosheath. And what you get from the flux is the thickness of the inner heliosheath, and with the solar wind changes as over time, you get basically a depth information. When does that arrive at the front? That's where the heliosphere is the smallest. And if you go further and further to the tail, you see any changes over the solar cycle, they arrive last. So that has become available now after we have a full solar cycle of measurement. So yes, I think to a certain extent, we get the shape of the termination shock, not all the way into the tail, because in the tail it's so thick that you have other effects going on that basically diminish the ENAs, and you can't get a thickness information there. But for the front, you can get the thickness information because we have a ground truth with Voyager 1 and 2, where we have local measurements, and then you take basically the arrival time of the changes all around, and you scale the thickness that you get from the fluxes of the ENAs to get the heliosheath thickness in comparison with the thickness where the Voyagers went through. That's kind of the task that I see. And in order to do that well, you may not need the resolution of IMAP, but you need the long time. You need several solar cycles, and we hope to have a comfortable overlap between IBEX and IMAP that we can cross-calibrate and then basically take our data products and have them over a long time.
You know, NASA has been talking about having an interstellar probe mission, but still going in the nose cone region.
Yeah.
Then in order to really to pin down the three-dimensional structure of the heliosphere, would it be worthwhile to go to have another mission going to other directions?
I think the first thing that would be very important is to have ENA measurements on the interstellar probe, and basically measure the ENAs perpendicular to the trajectory.
Mm-hmm.
And what you then get is you get a tomography of each layer as you go out, together with the measurement from 1AU. So of course you will have to guarantee that when you have the ISP going out, measuring perpendicular to the trajectory, that you still have emission at 1AU or at L1 better, that measures radially outward. Yeah.
Okay, I think we should talk about that more in detail in some other time. And from your slides, from the quotation you make, I think Eberhard, you're completely Americanized now.
Am I?
Yeah, you Steve Wonder for Ribbon in the Sky.
Yeah.
Okay, great. Any questions from the audience? The expert in the audience. Ming, I think you know Ming, right? Ming Ko.
Yeah, yeah.
He has a question in the chat box. Or Ming, can you just ask Eberhard?
Oh, hi.
Right.
I just wondered this very local magnetic field measured from the experiment. Are they the result of the cloud that you mentioned, that the collision between the two, because they are just crossing each other? And would it cause the direction of the magnetic field that you observe here?
So for the direction of the magnetic field that we are getting from IBEX with the ribbon agrees with the magnetic field where you can do the anisotropy of the. Oh, did I?
That's all right.
Can you? Yeah.
Yeah.
So what happened is the computer all of a sudden went to sleep, so I had to wake it up. Sorry. So as I showed, that agrees with that, and I showed you that all the measurements of the ISN flow direction the deviation that we get for the secondary components and the deviation of the hydrogen neutrals, which is a mix of primaries and secondaries. They are all along the same line that connects in the sky the ISN flow direction and the magnetic field direction that we get from the ribbon. So that's called by the modelers either the deflection, hydrogen deflection plane, or you name it. So that fits together. What at the moment doesn't fit with that is the direction that is locally measured by Voyager. So there, it had looked like that it was slowly coming towards the direction that IBEX said, but then there were some CMEs that where you see that also into the outer heliosheath that was jerking the direction basically back. What I have heard recently is that there is a debate about the calibration of the Voyager magnetometer measurements because the Voyager magnetometers originally weren't built for such low magnetic fields. So that was a mission to Jupiter and Saturn. So that it's now so far away and measures such low magnetic field, it's incredible. But there is one direction that is really hard to get. So that debate is not finished yet, so I don't want to say, but there is this discussion that this doesn't fit. The general magnetic field direction in our neighborhood, Priscilla Frisch has worked on that and written several papers. Those directions fit also within error bars with what we are getting from the IBEX ribbon measurements.
All right, thank you.
All right, good. Thank you. Other questions from the audience? So this gentleman, you have questions?
Yes, I have a question about IMAP mission.
Can you tell us your name first and your
Yes,
affiliation?
yes, sure. I'm Wen Yali from National Space Science Center. It's a institute belongs to Chinese Academy of Science, and actually I'm from Earth Manosphere community, working on connection physics about Earth Manosphere. So I have a question about IMAP, which is that so according to your several final slides, the IMAP will be at the L1 point. And it will provide some solving conditions for Earth Manosphere community that will be really great. So L1 is always important for us.
Yeah.
And I have a question that I didn't see the field of view ENA measurement from IMAP. Will that be possible for IMAP to measure some ENA signals from Earth or near Earth Manosphere environment? So why I ask this question is for Earth Manosphere or Earth atmosphere, we also have a large exosphere and with neutral atom, and so it's a kind of possible object if we compare with this interstellar neutral particle, but it's much closer, and I guess we can get some signal from Earth or near Earth environment, and maybe it can be possible for IMAP team to test or to check the ENA generation theory, because for Earth Manosphere we have many tens of spacecraft like MMS and Themis. We have lots of information about that. Yeah.
So That is going on already, and the better bet for that is IBEX, because IBEX orbits the Earth, and we for certain orbits, depending on where it is. So if it's on the front side, then basically the field of view goes through the front magnetosphere, and there are papers about the front magnetosheath. There are papers with the viewing of the tail. So if for half a year, basically, the orbit tilts back towards the tail. IBEX is a mission that's geared towards heliospheric physics, but we are not throwing away the data of magnetosphere, and quite a number of those, they are publicly available from IBEX. And we will continue to provide those data. As far as IMAP is concerned, for IMAP, the Earth is opposite of the sun, so 180 degrees away. The ENA instruments, they are looking mostly sideways, but we are getting the full sky going around the sun, but we're not looking backwards. In principle, we could do that with IMAP low, pointing backwards. It's on a pivot platform, but pointing straight back, the science is very limited for that. And then the Earth by itself is kind of a bright spot. So that's, we're worried about that. IBEX or IMAP high will look at 90 degrees relative to the sun and 45 degrees backwards. So it will miss the Earth. And the two IBEX IMAP Ultra heads, the very high energy one, is also basically up to, I think, maybe 30 degrees away from the Earth.
Okay, thank you.
But IBEX, so if you want that, if you send me an email, I can send you a number of papers or point you papers of IBEX ENA data on the magnetosphere. And,
that would be great.
That if you connect with people like Maya Dae, Stephen Fuselier at Southwest, they have the magnetospheric data, and then
Yes, actually, for me, that I got connection with Steve Fuselier when I doing MMS. I mean NASA MMS mission, and
here is the connection.
Yes, that's the and. I can probably use 1 or 2 minutes to give a brief introduction of China ENA measurement. Can I, Win? Yeah. So I think
you're probably speaking into mute.
Sorry, I said Eberhard, do you have time, right? I mean, just
okay.
Yeah, for me,
even though it's late at night now.
So personally, I'm so one part of my job is working on Earth's atmosphere, and also China has a planetary mission like Tianwen-1 in future, probably other missions, and right now we have a Tianwen-1 mission for Mars, and ENA science is also important for Mars space environment. And actually, from my institute, we had a payload for Tianwen-1 mission, which is called MIMPA. And we just finished our calibration in Bern University, Mephisto, this team there, and they had a lot of interaction. Yeah, we had a great time there.
Good.
and they had a lot, talking about IBEX, also IMAP, and the future IMAP calibration, and yeah, that's looking forward to have more, discussion with ENA community from US.
Okay. Yeah.
Yeah.
That
Okay.
is certainly be great.
Okay.
All
Thank
right.
you.
So that's
for
what
your
you want to
answer.
say? Anything more?
Yeah,
You
that's
could
the
say you
thing
want
I
to show
want
a
to
couple
say.
of slides.
Yeah. Yeah. Wonderful. Thank you.
Win, could you?
Janice, can you give Professor Lee the permission to show his slides?
Oh, okay.
You mean I can? You mean right now?
Yeah, we say you just said that you want to show a couple of slides, or you want to use the clip.
I didn't say I not
No,
this
no.
slide probably. I just let let people
Yeah.
know that in China we had a ENA instrument around the Mars, and then this year we are going to have another ENA imager instrument around Earth. It's basically focused on Earth's atmosphere physics, and looking forward to have more discussion and comparison with IBEX and other ENA instrument from international communities.
Very good, wonderful.
Okay.
Thank you so much, and good luck.
Yeah.
And any other questions? If not, that you could always write your comment or question to Professor Möbius, and if you don't his email address, you could write it to me, and I will send it to him. Otherwise, we'll close the session because it's almost 10:30 now. It's getting very late.
Yeah.
Okay, Eberhard, thank you so much again, and have a sweet dream. Sweet dream tonight. You sleep well.
Thank you, Wing.
Yeah.
It was
Okay,
wonderful. Great. So thank you for the opportunity.
Yeah. Good night.
Goodbye.
Yeah. Bye-bye, everybody.
Bye.
Thank you.